Okay.
Logging in.
Okay. You can go.
Okay, so good afternoon, everyone. Welcome to our last seminar of this season 2021-1. Today, our guest is Dr. Marc Huertas-Company. He got his PhD degree in astrophysics in 2008 from the Observatoire de Paris and the Universidad de Granada. He's now an associate professor of astrophysics at the Observatoire de Paris and the University of Paris, and a two professor at the University of California in Santa Cruz. Since 2015, he's also a member of the Institut Universitaire de France, and he's currently in the Canary Islands, spending 3 years at the Instituto de Astrofísica de Canarias. His research expertise involves the formation and evolution of galaxies, focus on the formation of massive galaxies and the morphology of galaxies in the context of large cosmological surveys. And today he's going to tell us about tracking morphological transformations and quenching with deep learning. Marc, thank you very much for accepting our invitation, and you can start whenever you want.
Okay, hello, thank you for inviting me. It's a pleasure to be able to present my work, which is in fact the work of several people that you can see below, especially students and postdocs working with me over the past years. So I decided, so the initial talk I was planning was more of a technical talk about how you use deep learning and machine learning in general to estimate galaxy morphologies. I've slightly changed my mind while preparing the slides, and I decided to do something more focused on the physics and how you can use machine learning to try to better track down how galaxies change morphology and how they stop star formation. Okay, so I think I will go rather quickly with the introduction, hoping that the majority of you are familiar with that. So we're trying to understand how the current population of galaxies emerge, and one of the key results of the past decades by observing large numbers of galaxies is that there's a bimodality in the local universe in which we have disk galaxies and bulge-dominated galaxies, in which we call originally the Hubble sequence, but it's in fact a sequence in star formation range. We now know that this bimodality in morphology is also tracked by modality in star formation, in which disk star formation typically happens in disky galaxies, and non-star forming galaxies are red and dead and have an elliptical morphology. And so the goal of lots of research in extragalactic astronomy is, and it's remained the same for many years, is trying to understand how this bimodality emerges across cosmic time. And you can track these with lots of different approaches. But at the end, what we try to understand is the origin of this diversity of galaxies and bimodality we observe. And so this is, translated in a modern way in what we call the main sequence of star formation, or the star formation mass plane, which are two key quantities of galaxies, and in which you can see that, the x-axis is stellar mass, y-axis star formation rate, and you can see that galaxies tend to be in what we call a main sequence. So they given their mass, they have a known star formation, let's say in a sort of power law, which is, telling you somehow that star formation must be regulated somehow. So it's not a stochastic process. And this, comes back to the idea of, that gas is fed into galaxies. And you also have this population that I just told you about, galaxies which are not in the main sequence, which are orders of magnitude less star formation. And in fact, those are those which are quenched, we call, or stop star formation. And we see that this is where the relation between star formation and morphology stands, where these galaxies in the main sequence are typically disk dominated, and these guys are more bulge dominated. And so, and one thing that we have learned over the past years by, this was in the local universe, but even if you go at high redshift, so when the universe was much younger than today, even more than less than a half of this current age, so down to redshift 3, this bimodality is still there, right? This is another way of showing it, but basically you can always see that there is a population of star-forming galaxies and a population of quenched galaxies, which typically are more massive as you go at high redshift, but this is also because of the completeness. And so this, this bimodality is, happening, is something that this process or this coexistence between these two populations is something that happens basically in all the time of the history or the history of the universe that we can probe. And so which means that the physical process that explain this dichotomy has to be in place for a long time. And of course, if you go at high redshift, you also see that there's the bimodality in star formation is also tracked down by bimodality in morphology. This is another way of seeing it in terms of scaling laws. Basically, what we plot here is mass and size of galaxies. You see that galaxies which are quenched, which do not form stars, are typically more compact, which are smaller at fixed stellar mass than the ones which are star forming, which is another way of seeing that the morphology of these guys is more extended and this is more compact. So the process that change morphology and at the same time and change star formation seem to remain the same or at least are happening at all cosmic epochs that we probe. And so what we're trying to understand is how this process take place and what essentially what are the tracks of galaxies and how galaxies move into these planes at different cosmic epochs is one of the key questions I would say in galaxy formation, is trying to understand how galaxies evolve into these planes that we observe. So putting we observe some fixed snapshots of galaxy properties, and what we try to understand is how these properties evolve and how basically objects move into these planes, which means how objects stop star formation and what are the tracks that they follow here, and at the same time, what are the tracks that follow in the structure that make that at the end we end up with a population that we observe today. And in fact, this process of quenching star formation is a fundamental mechanism in our universe, which helps explaining the properties of galaxies we observe. And in fact, when we study the properties in terms of stellar mass of galaxies, we see that the baryonic mass function doesn't track down. I mean, it's the dark matter halo mass function, which comes from simulations. And in fact, what you see here is that at the massive end, which is the mass I've been discussing so far, you see that there's a lag. So the star formation stops, and you see that the galaxy is completely dominated by dark matter because some processes are preventing a star formation, which is this quenching. So, as I said, in the observations, we can have these fixed snapshots of properties of galaxies. At the same time, things are evolving from the computing point of view, and we are able now to run cosmological simulations in large volumes in which we can plug in initial conditions and some physics of gas, physics of gravity, of course. And we can make galaxies evolve across time and follow how these different quantities change. And so basically we can connect or have a movie of how things assemble. Now, this of course has lots of caveats. Simulations are not perfect, and there's assumptions that are made. We plug in some subgrid physics, but in some sense, it's a way of being able to follow how a particular object evolves across cosmic time and follow what are the the different transformations that happen. And so basically what we have been trying to do in the past years with different approaches is trying to see if by following from a data-driven perspective, it's possible, to constrain from fixed snapshots that we get in the observations of morphologies and star formations by using information that comes from simulations, which is a dynamic information about how things evolve, and of course, but can we get some clues on what are the physical mechanisms that end up in the current distribution of galaxies that we observe? And of course, this is a tricky business because on the one side you have simulations that are incomplete and not perfect, of course, and on the other side you have noisy data with limited resolution, and you try to understand if you can first things agree and if you can learn something from these simulations about the physics that you get in the observations. So and we try to do these from a data-driven perspective, and the way we've been the procedure that we've been following the past years is to try to forward model simulations, which typically are in 3D, into the observational plane to create some mock observations. So we observe the simulations and put them at the same with properties as observations, with the advantage here that what's the formation history of these simulations. And once you put them at you forward model them, you can compare them at the same level and try to understand and try to establish some connections and try to understand or constrain the physics that's going on in the observations, or finding the physical mechanisms that are more compatible with the observations, which should be the ultimate goal. And so if you go into this direction, which is trying to find the evidences from a physical process that happens in the simulations, and try to find it, understand if this physical process is also happening in the observations. This is what we call simulation-based inference, in which we try to, by sampling from the simulations, you try to understand, see what's the physical or more likely physical process that can explain your observations, which is of course is extremely complicated because there are lots of physical processes going on, and there are many of them, as I will show you, are degenerate. So it's not that you can easily find a physical process that observe your observations. But this whole world of simulation-based inference, I believe, is something that will allow us in the future to understand a bit more and constrain the physics here. And I will show you some examples. If you go into the other direction, so basically you are trying to get information from the observations and then look for this information in the mocks. Then what we're trying to do is checking simulations. We're trying to see if, in fact, these guys live in the same space, or if the main properties that you observe on observations are reproduced by the simulations, which is also an interesting thing to do. And in fact, it's something that you need if you want to do some simulation-based inference, because if you find from the first place that these things are completely different, it's unlikely that you can infer some physical processes over here. So what I'm trying to do in the remaining of this talk is show you, this is basically the big picture and what we're trying to do. And I will show you some examples of things that we have and different methods that we are using from this data-driven perspective to do this bidirectional comparison between observations and simulations at the pixel level. And so basically, the simulations and the observations that we're going to use in this work, I'm going to use large volume simulations, hydrosims like the TNG suite, which is basically 1 kpc resolution, Horizon AGN. These are typically 100 megaparsec boxes with intermediate resolution. And I'm going to use as well what we call zoom-in simulations. Within that particular case, we focus on a given halo, but we get a much better resolution. And this allows us to resolve the internal structure of galaxies and probe the internal structure of objects. And I'm going to use surveys, essentially imaging surveys, big surveys like at low redshift, Sloan and similars, HST surveys at high redshifts, and also I'll say a word about integral field spectroscopic surveys. And so these are the data sets that we're trying to compare in this. So first thing that you want to do, and if you want to do some simulation-based inference, you want to check how good, and you want to understand how the morphologies change. First things that you want to do is, do we get the right morphologies? Do current simulations observe or get the right distribution of galaxies? And this is something that has been a problem for many simulations for many years. Getting the right morphological distribution of objects, or even getting a disk at low redshift, was a problem. And so basically this has prevented that really using information from this simulation to learn anything about how morphologies emerge. So this has been changing, as I will show you now. And so basically what you want to do is check how simulations reproduce the morphological properties of galaxies in the local universe. And again, here we follow we compare these at the pixel level, so we can generate mock images. And so basically what we do is we take images from the Sloan, so a low redshift, and we classify them using a standard convolutional neural network. And so that we get an estimate of morphologies at the pixel level. So you can do this more or less detailed, going to the bar level or just getting global morphologies. And then what we can do is, you mock simulations from the TNG cosmological simulation. You create mock SDSCS galaxies, and then you apply these models that you have trained on observations to see to the mock galaxies and try to understand if you get the same diversity and at what level you get this diversity. So if you do this, this is what you get. And so basically here we classify it only on 4 classes. So these are all TNG galaxies. So and what you can see in 4 classes, so ellipticals, early zeros, early spirals, and late spirals. And you can see that you see this morphological diversity. So you see objects in all 4 classes that these classes are calibrated on observations, and you see that this diversity of galaxies moving from the very early type to the less and more clumpy objects. And actually, if you look at the abundances, which can be probed by the stellar mass functions, you see as well that simulations and observations. So here simulations, dashed line are observations. These are for late type systems, early type systems. The mass functions track rather well. So not only you reproduce the diversity, but also the expected abundances of the different types of objects. This is in the local universe. And you can also look at how the sizes or the scaling laws of different morphologies have reproduced in terms of stellar mass and size or effective radii. And you can see that although there are some scatter, you also get the right normalization. So you get the visual morphology or the detailed morphology correct, the scaling laws as well, and also the abundances, which is a major breakthrough for these cosmological simulations. But in our case, it allows us to say, okay, we get the right morphology, so maybe we can then go back in time and try to understand how this happens in the simulations and see if it's compatible with observations. I'll go back to that. So before we do that, we need to highlight because some limitations of these, and these are inherent limitations of supervised learning. And in fact, what we're doing here is trying to training these CNNs on observe and then applying to simulations. When you do that, you are assuming that the simulations contain the same boxes on the same categories. Okay, and this is a strong assumption. It's, you know, you can be in a situation in which if you train your machine learning algorithm, your CNN, with cats and dogs, and then you try to apply it to an image which is outside of your training set. If you don't have a precise quantification of uncertainty, which is not always the case in machine learning, you can get you will get a label, but this doesn't mean that this, you know, represents your training set. So you can be in this situation in the simulation. So you want to go even further and test, you know, how close are you know, the simulations from the observations, but without imposing any category. And you can, so basically, how can we further check that? So do these live in the same manifold, let's say? Do they contain the same diversity? And so to do that, you need to go beyond supervised learning, and you can do this with generative modeling. This is work done with a student this year. And basically what you can do is trying to understand with this kind of generative modeling. I'm not entering into details because of the lack of time, but essentially you want to understand if, you know, the probability distribution of an observed galaxy in terms of at the pixel level, so probability distribution of the pixels follows the probability distribution of simulated galaxy. And so this means this is probing from a completely unsupervised way if the diversity of distributions that you get in the observations are reproduced by the simulations. And again, I'm not entering into details of the technical details, but you can ask me questions about that. We used in a particular case generative models which are autoregressive. So in that particular case, pixel CNNs. And so basically you can use these models to estimate the probability, the joint probability of a given image with the properties of the Sloan. Okay, and so then you can get the mocks from the illustrious and TNG, and then estimate based on the probability distributions that you have learned on observations, how likely they are, that how likely it is that these simulations come from the same probability distribution. Okay. And if you do that, again, I'm going a bit fast here for the sake of time, but you know, as I said, I'm trying to show you some experiments. But if you have questions afterwards on any specific case, I can answer and go into more details. So basically, what you can see here, so you can probe what's the likelihood at the pixel level that observations and simulations live in the same space. Okay, and so basically, without entering into details, what you're seeing here is this likelihood. And so you can, so you have several lines here for different simulations and for observations. So basically what you want to look at is that the closer the line of the simulated line is to the observations, the better, or the better it matches. So you can see here that you see a gradient here from different simulations. So the old illustrious simulations, which is older than TNG, is the worst in terms of morphology, in terms of likelihood. And as you get into the more recent models, you get closer to observations. And the best one is the one which has higher resolution, which is the same model, but better spatial resolution. This said, so you see that models are getting better into getting the morphology, and you can measure these without any a priori knowledge, just by throwing in the pixels. But one thing that you can see as well is that none of the models really matches completely the Sloan. So a neural network is able to tell you, wait, these images are similar but are not the same. Okay, and so this is another way of seeing it. So we are getting there. We see the same classes, but it's not exactly the same. However, there's a good fraction of overlapping. And so you can use still, and with some caveats, these to try to understand or learn how these morphologies have emerged. We are just, you can use other unsupervised ways of doing these. And now we are using, instead of generative model, what we call self-supervised learning, to try to do the same similar study, but now using not only photometry, not only images, but now data from MaNGA. So MaNGA is this IFU survey that for every pixel in the galaxy, it gets a spectra spectrum, so you can get properties like velocity dispersions, rotations, ages of stars, and metallicities. And so you can now probe, again, following the same approach, creating mocks of manga, trying to probe how these detailed properties of stars are reproduced by the observations by looking at them in some reduced dimensionality space. So this is ongoing work. First paper has been published, but we are now repeating these on simulations. Again, I'm happy to discuss a bit about self-supervised learning if you're interested on that. I think it's a very exciting approach. But since I wanted to focus more on physics, I want to try to extend this at high redshift. So remember, what we try to understand is how these tracks and how these morphologies emerge across cosmic time. And one advantage of the simulation is that you can indeed go back and trace how things change. And so you check basically on the one direction that you get more or less the right morphological distribution, and then you want to see how how you get there, how in the simulation you get there, and if these tracks that you get are somehow compatible with what you would observe. So in order to do that, we can repeat a similar study, but at high redshift. So now, instead of comparing to Sloan, you can compare to candles and see at different redshifts how the morphological properties of galaxies at fixed snapshots are still reproduced. So we are still on the direction of trying to check simulations. For that particular study, we used the TNG50, which is the same TNG model, but better spatial resolution. So you can look at less well-resolved galaxies by HST. And again, you can see here CNN classifications of mock TNG50 galaxies and candles in 4 different morphological types. And again, you see that once you add the noise, the HST, PSF, and so on, they are remarkably similar. Okay, so even at high redshift, these are typically galaxies at 1.5, 2. You get similar diversity. You get these compact objects. You get these extended disk, clumpy disks over here. So if you look carefully, you can start seeing some differences. Like, for example, the disks here appear to be thicker than the simulation, than the observations. Probably an effect of resolution, but it's remarkable how these simulations are now reproducing the diversity even at high redshift, where again there's no particular fine tuning. And if you quantify these in terms of star forming and of fractions, so these are fractions of different morphological types. Again, it's a bit difficult to read this plot, so I'll just give you a hint of the main result, but essentially what we're plotting here is fraction of different morphologies, bulges, disk, irregulars, and disk spheroids as a function of stellar mass for different redshift beings. Okay, these are star-forming galaxies in the observations and in the simulations, done exactly with the same method on both. So CNNs trained on one and applied on the other. And basically what you can see is that, qualitatively, you get more or less the same trends, which is that at high redshift, you are completely dominated by what we call clumpy irregular galaxies. And you can see these, that it's basically the same in the simulations. And as you go at low redshift, you start seeing the emergence of disks for the star-forming objects, okay? So without any sort of fine-tuning, you see that the same trends appear in both once we compare the same resolution. And if you look at the passive galaxies, or quenched galaxies, you see that these are in both dominated the high mass end, but spheroids or things with bulge. So this dichotomy that I was talking at the beginning that you observe at high redshift, simulations are also reproducing it. So passive galaxies tend to be bulge dominated, and these more or less with the right fractions as compared to observations. And so basically, this is somehow validating the idea of even if not perfect, you can try now to see how these emerge in the simulations. And so another way of checking it again is you can look at the scaling laws. So in that particular case, I'm looking at the central density of galaxies versus mass. And again, and so these are simulations in black, observations in yellow, and you can see that they match relatively well, so with some discrepancies, but basically you get the right normalization and more or less the right scatter. And more importantly, what you get is that at a given mass, passive galaxies, what you see here at different redshifts, are typically more dense than star-forming galaxies. So this bimodality in morphology and star formation is also seen in the simulations, and you also see the right fractions at different cosmic epochs. And so basically, again, when you compare apples to apples. So, and so now the next step is going in the other direction and trying to do some simulation-based inference. So trying to learn if, more or less, I can get the right properties. Can I learn on how I go back to the simulation, which I cannot do in the observations, and tracking back in time the progenitors of galaxies and see how they move into these planes, which was the main question I was asking at the beginning. And so this is an example of this in the TNG50. We are looking at evolutionary tracks here. This is from a recent paper by a student, Sid Varma. And what you can see here is, so I will spend a little bit of time explaining this plot because it's a bit complicated. So what you can see here is the stellar mass and the central density. Okay, so basically, the higher is the central density of stars, the more likely there's a bulge, so it's more elliptical, let's say. And this is stellar mass. And what you can see here is two tracks. So these are of galaxies, so progenitors evolving in the simulation in this plane. Okay, and so you see two tracks. One is progenitors of star-forming galaxies at redshift 0, typical mass of Milky Way mass. And red line is the progenitors of objects that are quenched, okay, at redshift 0 point when I observe them, okay, and then you get the symbols here, which is the morphology that we inferred from the images, okay. So basically, a diamond here is an irregular galaxy, and then this is a bulge-dominated galaxy, okay. So when you look at these tracks, so that go from here to here, what you see is that galaxies more or less evolve growing in stellar mass. They grow a little bit the stellar density, and they remain sort of, irregular, clumpy up to redshift 1-ish, more or less. Okay, and then something happens here when, for this particular population, which is the quenched one, they rapidly change morphology below redshift 1, and they become bulge dominated, and then they quench, and they go to this scaling law, which is the observed one, to match, and you get this fact that quenched galaxies are denser, and you get it below redshift 1, at least in the simulation. So what happening here is that you get this morphological transformation, and then you quench, but this happens at rather low redshift. And before that, both have very similar trajectories here, even if you remain star forming. And so next question is, what is causing this transformation in the simulation? The answer now is strongly simulation dependent. Okay, so, and this is where things start to become complicated because you get, okay, I'm getting the right observables, I'm getting an evolutionary track, and one particular problem with our field of galaxy formation, and it is something I will try to emphasize towards the end, is that there are many ways to get to that particular configuration. So this doesn't mean that this is what's happening in the observation. It means that this is a mechanism that could get the right distribution in the observations. And so what is the mechanism here acting? And this is not completely trivial, but in the TNG simulation, it's strongly related to the activity of the supermassive black hole that is at the center of galaxies. And again, I'm showing here with another scaling law, which is central density, so same quantity here, which measures how elliptical you are essentially, and then the mass of the black hole. And you can see here that in the TNG simulation, you have two different regimes, okay, in which when you are an irregular galaxy, what's happening here is that you are increasing a little bit your central density, but not that much. And what's growing very quickly is your black hole, okay? So a black hole is accreting fast. And you remain an irregular galaxy. And at some point, what happens in the TNG model, when the black hole reaches a critical mass, the accretion gets lower, and the black hole starts ejecting and becomes, the feedback from the black hole into the galaxy becomes ejective, and it very efficiently quenches the galaxy. And you can see it over here that when you change the regime of the black hole doesn't grow that much. Then the galaxy starts quenching, and at the same time you start transforming your morphology. Okay, so it's at the moment when the black hole changes its activity mode and gets ejective, it is where you transform your morphology, and it's where and when these galaxies quench. And this increase in sigma-1 without increase of the black hole, this is what gets you into this relation. Okay. So why the central density is increasing at that particular moment? So this is a good question, and you can summarize it here in that particular plot. And so basically, I'm showing again the same thing, a bit complicated, but basically now this is as a function of redshift, and these lines are showing different quantities. So we're showing here central density over here, so the sigma, and here I'm showing the black hole mass, and then here I'm showing the gas mass, okay, in the center. And so basically what you can see here is these two regimes that I'm talking about. First, the galaxy is star forming, and it's irregular. At this particular time, the black hole grows very fast, okay? And sigma-1 and the central density grows, but the morphology is still in an irregular galaxy. When the black hole changes its regime, it stops accreting, feedback becomes ejective, and you can see that gas is depleted super fast. So you don't have any more gas in the center, no more gas for star formation. However, you start seeing an increase of sigma-1, which is a bit, and this is where you transform your morphology. Now, this is a bit puzzling because it means that the increase of stars in the center, the central density, is not driven by star formation, because you see this increase when the gas is being depleted. Now, what is causing this? We still don't know exactly in the simulation. It could be that because you're ejecting the gas, the potential is redistributed, and then stars are redistributed and you increase this density. However, I would naively expect that the effect should be the opposite. And it could also be that there's some fading of the stellar populations that it's happening here. So it's something that we are investigating. But in any case, what you predict from this simulation is that you have these two phases, and that the morphological transformation and quenching happens at low redshift when the black hole, central black hole, changes its regime. Okay. And I see that I'm running out of time, and I had a lot more material. So what I wanted to, but I think I will have to shorten the talk. So what I wanted to emphasize now is, this part of can we now check in the observations if what are the conditions of these phases here, and what we can learn about how disks grow in that particular region, and how this transition happens. But now, probing by simulation-based inference some particular physical processes, and see which one would explain, for example, the growth of disk in that particular region. I'll try in a few minutes to show you an example of these, and then I think I have to skip this phase over here. And so we've seen that you have this clumpy regular phase above redshift 1-ish, and which is what we see in the simulations and also in the observations. So you see at the morphologies of these high redshift disks look something like that, with extremely irregular and lots of big clumps. And so there are different ways that you can explain or you can model the growth of these objects here in this clumpy phase. You can argue, or there are models that tell you that these clumpy structure, in fact, governed by the physics of the interstellar medium, and which what you're seeing here is just that, gas disks are extremely gas-rich, they are turbulent, and so therefore you form these clamps that are able to migrate and build stellar mass in the center, and that's the way you increase your central density, by essentially governed by in situ star formation fed with gas from the cosmic web. Or you can say as well that these perturbed morphologies that you see over here in this particular phase are the consequence of lots of minor mergers activity that is happening at these redshifts because the universe is more dense. And in fact, what you're seeing here is that the assembly of disks in that particular phase is governed by mergers. And so this is something that we can try to test, and by now doing simulation-based inference. So going from the simulations to the observations, because you have in the simulations, you know what's the origin of the different clamps. So you can apply this knowledge, use machine learning to try to see what are the conditions of the galaxies we observe. Okay, and so one way to do it, and the theory predicts that when you measure the clamp, you measure these clamps, the clamp stellar mass function of. So now we are looking at the resolved morphology of objects. Clamps that are formed in situ, so by star formation in the galaxy, follow a clear slope in the mass function of -2. Okay, and they are typically less massive than 10 to the 8. However, more mass clamps above this mass, which are formed are typically formed ex situ, so they come from mergers. Okay, so see if you are able to from this knowledge from the simulation, try to get understand what are the origin of the clamps. You can put some constraints on how observed disks are evolving at these redshifts. And this is something that we are undertaking in these two papers by Omri, a student working with me, and Avishai Dekel, and a paper of mine from last year. And this is where we do some simulation-based inference in the sense that we are using now zoom-in cosmological simulations with very high spatial resolution. And you can go to the simulations and actually in 3D detect these clamps. And from the simulations, what's the origin of the clamps. First, that it's actually a physical clamp, and if it comes ex situ, if it comes in situ. So you can train a neural network on the mocks from the simulations, or going in the other direction, and in 3D where are the clamps, and you teach this neural network to, from the 2D images, identify the positions and the stellar masses of the clamps in the 2D image. Okay, here we are using standard CNNs and encoder-decoder networks for those who know how these work. And for the sake, I don't have much time, but if you can do that, so you can get true clamps from the observations based on informed from the simulations, and then you can get the stellar masses of these clamps and compare the stellar mass functions. Okay, we are still going through a summary statistics for interpretability, but which is a stellar mass. You can do this at the pixel level, but in that particular case, we did it with a stellar mass. And what you can see, if you plot now the observed stellar mass of clamps as compared to the simulated from in situ clamps, you see that the observed clamps that you get in candles are way more massive than what you would predict from an in situ formation of clamps. So this is somehow you would conclude that the majority of clamps that you observed in candles are in fact most likely formed ex situ. So it would mean that you are seeing lots of mergers happening in these galaxies, and not in situ formation of clamps. But this comes an issue in that the clamps that the mass function that you get here is from the idealized simulation. If now you say, okay, I'm going to do the same analysis on mocks, on images of the simulations, this is what you get. Okay, so from the green, just by the observational biases, you get to the red. Okay, and so this again shows you the importance that when you compare observations and simulations, you need to do it apples to apples in the same conditions. Okay, so you see how bad you can get in getting the masses of the clamps, and this is because you get low resolution and you are biased by the background of the galaxy and you overlapping clamps and so on and so forth. And so basically you see that the fact that you observe this mass function is not necessarily incompatible with being in situ. And it looks like you could get this distribution just by observational biases. And so the clamps could be in situ and not formed by mergers. So what we've done here is trying to correct, and again, use machine learning to try to correct from this bias. And in fact, what happens is that when you compare the stellar mass of a clamp in the 3D to the stellar mass that you get on the 2D, you see that you get a factor of 10 difference. You see a correlation, but clamps in 2D are 10 times too massive than they are in 3D. And this is again for with limitations on the method how you estimate the masses and the resolution of HST. And this creates this effect over here. So you can use machine learning to correct from that. And here we are using a mixture density network with a Bayesian framework to correct from this stellar mass. And once you do that, you see that you are able to recover both in observations and observations a slope close to -2, which then gives you, points to the opposite conclusion, which is that probably clamps that you observe in candles are most likely, or for the most majority, formed in situ, which will tell you that the evolution of disks is mostly governed by in situ processes and not by mergers, which is also compatible with what simulations say. I will stop here, unfortunately, because I think I'm really running out of time. There's more on how you can use clamps to constrain feedback and programs on a future program on the James Webb. You might ask, what's about mergers? And we're also looking at mergers with machine learning and trying to see if you can pin down what's the effect of mergers and major and minor mergers. And this will be an exquisite science case for Euclid, in which I'm very much involved. I'm happy also to chat about that, but unfortunately I don't have time, and so I will go straight to the conclusions and apologize for the delay, for being too long. So I've tried to show you some ongoing efforts to use machine learning to link the theory of galaxy formation imprinted in incomplete simulations, of course, with noisy and also incomplete observations, and how these data-driven approaches allow one to start testing cosmological simulations at the testing level, at the pixel level, sorry. And so one of the conclusions is that recent cosmological simulation reproduce reasonably well the morphological diversity at low and high redshift, and also the bimodality in star formation. This enables some simulation-based inference, which can be used to probe and constrain the physics of galaxies without going to summary statistics. However, things are still very degenerate, and I didn't have time to go to that, but there are different evolutionary tracks that can explain the same observables, and it's not always easy to disentangle between them. So thank you very much, and sorry again for being late.
Okay, thank you very much, Marc, for the talk. For the people that are watching us on YouTube, we are going to stop our transmission here. We thank you very much for your participation during the semester. And